13.6 equilibrium calculations part 2. Now, on the worksheet this time, I want you to do number 1. So it's a different number 1, if you'll see on this worksheet. Number 1, number 2, number 3, and number 5. Now, this is something that I do because it's always a challenge in AP Chem to teach all of this material before the AP exam comes up. So what I do, what we've done on equilibrium, I've shown you gas equilibrium calculations. Well, there's also something called acid equilibrium, Ka, base equilibrium, Kb, and there's what's called solubility equilibrium, Ksp. What I'm going to do is I'm going to show you how to do the math of all of those, Ka, Kb, Ksp, just up to the extent to what I've shown you already on the gas laws. So the main thing, there's only one kind of gas law equilibrium that I haven't really shown you, and I'll talk about that when I do the problem. So what I've shown you, you will see that this problem looking the same way. I'll show you what I mean. Now in the next chapter, when we get to acids and bases and KSP, they call it, I'm going to go in even further and show you more about that. And we will review this as well too. So the first thing I'll do, you see it was actually the first problem I put in because it's normally the easiest problem and it's probably the most common ever asked on the AP is something called a Ka equilibrium. And here it says a 1.5 molar solution of acetic acid. Oh, by the way, so what I'll do is, I will ask you some of this on the quiz when we have our first quiz, our math quiz of this. But I'll let you know what to expect. I'll let you know what things are coming up. Okay, a 1.5 molar of acetic acid solution is prepared in the lab. Number 1, write the balanced equation for the ionization of acetic acid. And it says there's 2 ways to write it. First of all, for acetic acid, you can write CH3COOH. Now, when you add that to water, here's what you get. You get an equilibrium system. Water takes away an H. Every time you have an acid, HCl, HBr, C2H3O2. By the way, that is acetic acid. This is also acetic acid. But here, I've told you this in the past, I believe. This is kind of in the organic form. Both of these have been used on the AP, by the way. They use that form and that form. Okay? This plus this gives you, pull this H off and attach it to the water. It makes something called hydronium, or H plus 1. And you also get CH3COO negative. Okay, another way to write it, CH3COOH, and actually this is how I think I'm going to do it for right now for this chapter, and we're not going to focus too much, is you can write it this way. You can just say, well, the H breaks off, and behind you have left CH3COO negative. So there's actually another way I could write it with that equation too. If you want to see it, I'll show it. You're like, you're not saying anything. Okay. Well, all you do is you just say HC2H3O2 breaks down into, take off the H, C2H3O2 negative 1 plus the H plus that broke off. You can write it that way too. So all of these are acetic acid dissociating. This is like the most scientifically correct, well, but not the best in the world, but it's the best model we can get. Because the H doesn't just float around in the water, it attaches to a water molecule and makes H3O plus. So it makes water a positive. But H plus and H3O plus mean the same thing. And when you do your math, the number you get for that will be the number of that as well. Okay? So I know I'm telling you a lot of things, and this is another way to write it as well. And you can even write that one with H2O if you wanted to, and get H3O in that. Okay, I'm getting to be too crazy, and all I want to do is show you the math. So, in fact, let me just take that one away. There I go, trying to show you too much. But okay, so here's the equation. And now that I wrote the equation, I'm going to rewrite it. Well, I'm going to rewrite it over here. How many times can I write this thing? I'm going to write it to the side. So, in fact, let me do it right here. It doesn't matter. Okay, now because I'm going to be doing an icebox. I'm sure at some point. All right. Now number 2 says, oh my goodness, I did number 2. Write the balance equation for the ionization of acetic acid using the symbol. Oh no, I didn't do that. HA. There's no need to really write this, but I'll do it. It's on the paper. HA breaks down into H plus and A minus. If you ever see that, HA is like the general symbol for acid. H plus and A is the anion, the -1 anion. And I know some anions they're not all -1, but like chloride, Cl -1, bromide, Br -1, F -1, Cl -1, nitrate, NO3 -1, chlorate, ClO3 -1. But you said, but what about the ones that are -2? Well, when it comes to equilibrium, the AP only asks about those that have only one H, or they're called monoprotic, only one H. So you don't really have to worry about the other kinds. But anyway, but you could have another like H2SO4, but they've never asked, or they don't anymore. They don't ask that one anymore for the second ionization. All right, number 2. Here's the main thing: calculate concentration of H plus and the concentration of CH3COO negative in a 1.5 molar solution of acetic acid. All right. Well, first, I forgot to ask you to write the Ka expression. So to write Ka, it's equal to, remember, products of reactants. H plus molarity times CH3COO negative molarity over CH3COOH molarity. That's your K expression. Now they want you to find what is the concentration, what's the molarity of H plus and CH3COO negative at equilibrium. So to do that, we use the icebox. Now when it says in a 1.5 molar solution, what is the concentration? This is the same thing as in the gas stuff that we did before. You're going to write the initial molarity as 1.5 molar for CH3COOH. Now this is an interesting thing. So when we say, like, if I were to give you like CH3COOH molecules and say, okay, you weigh this out and this many grams and put it in the water and dissolve it. You know, molarity is the number of moles per liter. So if I told you how many grams of CH3COOH, you change gram to mole, then mole divided by liter. That will give you molarity. Well, okay, if you calculate the molarity, just say you prepare a solution. If I'm losing you a little bit, this is not going to be that important. But I just want to tell you, if you created a solution in class, you said, okay, I've mixed these together. This is 1.5 molar CH3COOH. Well, in reality, it's not exactly 1.5 molar because this is, once it's in water, it's going to dissociate and it's going to go down a little bit. So this is the same thing I've told you before. So even though we say, what is the concentration of H plus and CH3OO negative in a 1.5 molar? Really, here's what's going to happen. They start out being 0 in the beginning, okay, unless they tell you otherwise, and we'll get to that really in the next chapter. They're 0, so the change is some of this will break off. It's got to shift right. So minus X. This is going to be plus X. This can be plus X. So 1.5 minus X, X, X. Doesn't this look familiar? This is why I want to teach this right now, because it's the same, mathematically, it's the same thing that we did already for the gases. Now the Ka value is given to be 1.74 10 to the negative 5. You know, I always say 1.8 10 to the negative 5, but oh well, it doesn't matter. We can use this number. All right, 1.74. Oh, you know why? Because the Ka depends on the temperature, and we didn't state the temperature in this problem. But I think at 25 Celsius it's 1.8, but it changes with temperature. So, yeah, you might say, well, hey, in this problem it says 1.74, but I looked online or I saw another problem that said 1.82, because remember, it changes with temp. But they're not going to do a change in temp on you. Whatever they give you, use it. So 1.74 10 to the negative 5 equals H plus. Now remember, at equilibrium, the H plus at equilibrium is X. The CH3COOH is also X. And on the bottom, it's the acetic acid 1.5 minus X. And, yes, you get to do the same thing. Yuck, I hate that math. Okay, assume x is negligible. What a great thing we can do this. Maybe one day somebody has done this in their math class. The teacher, oh, this looks too tough. This whatever trig or whatever pre-calculus. This looks too tough. Oh, I'll just assume this is negligible. And now it becomes, and then they'll come after me. 1.74 10 to the negative 5 equals x squared. I'll go on and multiply those two. Divided by, and we're going to ignore that x. You could just say x times x over 1.5. I mean, technically you'd say this, oh yeah, I told you also it's better to even put approximately equal to x times x over 1.5. So what you're doing when you assume it's negligible, you're assuming that anything that's minus or plus, and it could be on the top or on the bottom, but anything after the minus sign with x or plus, it could be minus x, plus 2x, minus 3x, whatever. It doesn't matter. That's the part that goes off, so that way you have only a number. Now, just to save space on my chalkboard, though, I'm going to put those together. And I know I do this really quick a lot of times on the problems, and you might be, why do you do that? But I jump to that step, just because x times x squared. Okay, now we'll solve for it. So I'll multiply those two numbers, 1.74 10 to the negative 5 times 1.5. And then I get, okay, 2.61 10 to the negative 5 equals x squared. Then, of course, you get the square root of both sides. And x is 5.10. 10 to the negative 3 equals x. Molar. Now, let me double check again. 1.74 10 to the negative 5 times 1.5 equals, the square root is 5.10. Actually, 5.11 when I did it this way, but times 10 to the negative 3. When you leave it in your calculator, it might turn out different, or maybe I messed up, but it doesn't matter. 101. Believe me, it does not matter if the last digit can be up or down. I told you, like 2 or probably at least 2. So if I say 5.10, the answer, and you put 5.12 or 5.08, you'll get credit, even with the AP. Just make sure you put, the 3 sig figs. That's probably even more. Oh my goodness, bad fella there. It only has 2 sig figs because of that. Just make sure and I checked it. That only has 2 sig figs, so it should be 5.1. That should have been 2.6 even too. Well, they don't care about what you have on your work. Sig figs only matter in the very last step. So you can do that, and then the very last step, and you might want to do that because everything I did here was multiply, divide, or square root. And those are all the same count rule. 2 sig figs there, 2 in your answer. All right, now, before I move on, let's read the question and make sure we answered it. It said, calculate concentration of H plus in CH3COOH. All right, the H plus is equal to X. So that's going to be 5H plus. It's a good idea to write equals. And then CH3COO negative equals 5.1. Okay, this is really important, my students in AP right now in my class. When I grade your quiz, I know, and some of you are the nicest people and you work so hard, and I can see all the work there, and you stop it right there. But then if you stop there and didn't write these two down, I would not be able to give you full credit, okay? Because I don't know if you know that means this and this, okay? Now, if you want a little shortcut, here's what they do on AP. 5.1 10 to the negative 3 equals X. Then they put equals H plus equals CH3COO negative. If you want to write that down and circle it, you will get full credit, okay, for this problem. But remember, sometimes on a problem, so if you want to be lazy, at least write that down. That equals H plus equals that. Now, be careful, though, because sometimes, you know how it goes in the icebox. This might be a 2, or that might be a 3, and then you got to multiply and all that. So it wasn't here. But I'm just telling you to make sure you show me the work. Okay, so hopefully that wasn't too hard, and you can do the acid problem. So I gave you one of those on that worksheet. I just showed you a moment ago. And you could, if you wanted to pause it now and do the acid, you can do that. In fact, you could probably with each one. Now, I left my notes Well, I have some more notes of my own at school besides these, because as years have gone by, I've realized I don't need to go over all these examples of the gas problems. I don't know, I was going crazy with it. I put A, B, C, D, E, F, G, H. But instead, what I want to do is I want to do a base, and I want to do the KSP problem for you. So I'm going to give you a problem. I tell you what, I will try to put this in on your, I'll probably upload this as well. But since we're doing very soon, as I'm making this video, we are about to do the planning for the AP readiness to UCLA. And I have one of all of these on there. So I thought, well, why don't I just use that? So let me go, and I did an acid problem. I don't need to do an acid. Oh, but there's a really good base problem right here. And here it is. In fact, this came from an actual AP question. Okay, so here is the base problem from 1987. Okay, so NH3, long time back, plus, they give you the equation. How about that? Plus H2O gives you NH4 plus. Now, this equation, they give it to you, but it is good for you. By next chapter or later on, you need to memorize this. But ammonia and water come together to give you ammonium hydroxide, actually. When they come together, it's like a Lewis reaction. NH4OH is produced. So ammonia and water give you NH4OH. But however, because you're in water, this is soluble. All ammoniums dissolve, so you get NH4 plus and OH negative. Now, they give the equation to you on the paper, so you can use that one. And it says the KB the KB, it says, okay, on the paper, ammonia is a weak base that dissociates in water, shown above. At 25, the base dissociation constant, KB, equals 1.810 to the negative 5. So interesting, it's the same as the one we saw, 1.810 to the negative 5. Now, the KB is just the K expression when it's a base. Now, I'm not, again, in the next chapter I'll say more about it, but I'm not going to say a whole lot more than this. How would you know that this reaction is a base? This is a base because it results in hydroxide. If the water ends up having an excess of H plus, like the one I did a moment ago, H plus comes out as a product, it's an acid. If OH negative comes out, it's a base. So this is a basic reaction. Now it says, okay, so they want you to find what is OH at equilibrium. Okay, so the next thing that they would normally ask you is write the KB expression. All right, so KB, watch this. Just call it B because it's a base, but otherwise it's the same as any other K. These two things go on top. NH4 plus times OH negative. On the bottom, NH3. You don't put water on the bottom. Remember, it's a liquid. Did I tell you that? In the equation it tells you it's a liquid. But it's H2O liquid. Even if it were a gas, you wouldn't put it because all of these are aqueous. Aqueous, aqueous, aqueous. All right? So you put only aqueous in your expression. If that were a gas or a liquid, no matter what, you would or solid. I mean, it won't be a solid, but you are not going to put it in there. Okay. Now, the question is, what will the OH negative be at equilibrium? Well, just do the ice box, and I think you'll be getting good at this. It says 0.150 molar. So you got 0.150 molar NH3. Now, I'm not going to do the question that it talks about the percent. I'm not going to do that with you right now. I don't think, I should have shown you that on the other problem. I could have shown you that like as a bonus thing. Maybe I'll talk about it. We'll see. But, okay, well, it's okay. Here we go. Let me just do this. So 0.150 is going to be your initial. And, of course, you'll have none of this to start off with. We only want to look at the water. So the change will be 1 to 1 to 1. So remember, if there had been a 2 there, you put minus 2x. But it's not. There's no 2. But I'm just telling you, you always match stoichiometry 1, 1, 1. Makes it really easy. Minus x plus x plus x. 0.150 minus x, x, x. Isn't that like the same thing you've been seeing? Aren't you getting good at this by now? 1.8 10 to the negative 5 equals x times x. Looks like the same problem I just did a moment ago, doesn't it? That's only a couple of different numbers, but the same format. That's why I wanted to teach you this now, because it'll save time later and it gets you a lot of practice on all the problems. All right, so then, yep, assume x is negligible. Hope you got that right. Assume x is negligible. Some people say assume x is dinky, very small, or insignificant. So I'm going to just combine those again. It looks almost the same thing we just did over 0.150. Oh, and I also will change that to an approximate. I keep forgetting about that. You don't have to do that, but in fact, I once heard, and I won't bank on this, but if you put this, you can put that instead of saying assume x is negligible. That would count as that. But I'll always want to say assume x is negligible. I'm going to look for that when I grade your papers. But on the AP, they might be more lenient about it. But anyway, I'll do both. Okay, so 150 times 1.8, 0.150 is 2.7 times 10 to the negative 6 equals x squared. Now, let's get the square root of both sides. And so it looks like 1.6 10 to the negative 3 molar equals x. Actually, I've got this one worked out, so I just looked at the answer right there. Yeah, I got it right. Okay, so 1.6 10 to the negative 3m. Did we answer the question? Determine the OH negative concentration. And it is, yes, that is the OH, So that equals OH negative. That would be, I put brackets around that. I didn't do it. That would be the answer. Let me show you percent dissociation. I'll throw it in there because I could put it even as a bonus for the other question. Percent dissociation, there's something really important about this I want to mention too. All you do is you take, for this one, you take the OH negative at equilibrium and divide it by the initial NH3 molarity times 100. Now, why do we say percent? What you're saying is, what percent of this turned into OH? That's really what you're saying. So, if I plug that in, OH was 1.6 10 to the negative 3 divided by 0.150 times 100. Now, 1.6 10 to the negative exponent 3 divided by 0.150 is times 100 is 1.1%. Very small. 1.1. Only 1.1% of that breaks up. That's why it's a weak base, they call it. Okay. Now, it's good to know that, and it's also good to know, and I think I told you this in an earlier lesson, in college, you only can say assume x is negligible if this number is 5% or less. Okay? But for AP, it should always be 5% or less. When they make a question for you, it should be. One year it was more than that, and they still let it work out. They let it go. Now, if you want to do this for the problem I did a moment ago, which I forgot, I should have shown you on acids, it's more important. But dissociation for an acid, the equation changes. And you probably can figure out what it would change to. It would become the H plus at equilibrium divided by the initial H acid. So in that case, it was, what was it? CH3COOH. So if I took my H plus at equilibrium divided by the initial CH3COOH, which I think was, I don't remember what the problem on the paper was. Oh, well, I'm not going to look back at it. Well, then times 100, that would give you the percent dissociation for the acid. Okay, I might have to make a second video to do the other part. Yeah, I'll have to make a part. This is part 2, but part 2, I'll have to do that for the KSP. But hey, the good thing is you're going to know how to do all this stuff. All right, I'll get to the second part when I'm able.